All right, so section P7, it's all about solving absolute value and polynomial inequalities. I believe in P5 we did absolute value and polynomial equalities. As far as polynomial equalities is concerned, we just did quadratics, right? We solved by factoring what I like to call what I use is the Lizzie method. These are now inequalities. Oh, before I get too deep though, I only had one person ask me over Remind on the weekend, and it concerns me a little bit because it's a question that I would imagine caught a lot of you off guard. Specifically, I gave you an absolute value equality, and there was x's inside the bars and outside the bars. And when you solve that question, if you solved it the way that I taught you, you would have gotten two answers. However, because there was some x's outside of the bars, this could generate what we call an extraneous solution. And anytime you have x's inside and outside absolute value bars, you must check them to make sure they work, because one of the two answers was extraneous. So either you didn't check your answers, or, meaning with like an app or Slater, which is now moved to Quizlet, or you saw that you were wrong and just accepted it and erased one of the answers if you didn't contact me. Or 3, you were a baller, you need to check. I hope it was number 3. If ever you see that your answer is not perfectly right and you're not sure why, I'd like you to reach out to me, because I don't know which young lady it was. It might have been this class, might have been third period, I'm not sure. Asked me, so did I need to check my answers? And I said yes. That didn't come up in the notes. Whenever you're solving absolute value equalities and you have x's inside and outside, always check your solutions. Anywho, okay, so inequalities, rock and roll. First of all, I want you always thinking smarter, not harder. Absolute value can only give you what kinds of results? Just shout out. Positive. No negative results allowed. Why am I saying that? Well, let's just say, for example, this didn't say is less than 8. Let's just say it was less than -8. Students that know what they're doing don't do any work, and they go no solutions. There's absolutely no way that an absolute value is less than -8 because you cannot generate negative solutions. Same thing if it says equals a negative. Now, if you do the algebra and you set up the positive case and the negative case, you will get answers. And they'll be waiting for you on my test. But that doesn't mean they were correct. Always thinking smarter, not harder. Absolute values can only generate positive results. So is it possible that it's less than +8? Absolutely. Absolutely possible. So what we're going to do then is set up both our positive and negative cases the same way that we did on Friday. For the positive case of an absolute value equality, all you do is assume that inside the bars, the x minus 4 was a positive value. If it was a positive value, then the absolute value bars wouldn't have changed anything. Therefore, just drop them. They're not necessary in the positive case. And we'll solve for x simply by adding 4. And that will give me that x is less than 12. Cool. Now we set up our negative case. The absolute value inequalities is why I teach the method of changing all the signs on the inside of the bars. It's because of the inequalities. There's another way, and you may or may not have been taught the other way in the past. If you're comfortable with it and you're not going to goof it up, by all means use it. If you don't even know what I'm talking about, then just stick with my method, please. What we're going to do for the negative case is change all the symbols on the inside. So this positive x will become negative, and this -4 will become positive. And then we just get x by itself. Subtract the 4 from both sides. And right here, you have to watch out. I'm about to divide by a negative sign. When you divide by a negative number across an inequality, it will flip over your inequality symbol. So when I divide by -1, that less than symbol is going to become a greater than symbol. So what we have here, yes ma'am? Yeah, it is -4. I forgot my negative sign. Good catch, good catch. Thank you so much. What we have here is an overlapping setup. Because this says numbers bigger than -4, this is numbers less than 12. These overlap. So we can write this as a single solution set. I don't want to use inequality symbols. I want to use interval notation because it takes up less space, and it's what's going to happen in upper level mathematics when you get there because you're all going there starting next year. Since I do not have equal to bars, I will not use brackets. My interval notation will be parentheses only, where -4 and 12 are the boundaries of the answers, but they are not included in the answer set. Those are your answers. Every number between -4 and 12, not including -4 or 12. And there it is. Does it look like a coordinate? Yeah, it does. But because you're solving for x, you know it's not a coordinate. Yes, ma'am?
Wait, so when does sign flip? When you divide by a negative number?
Yep. Inequality symbols will flip over anytime you multiply or divide by a negative number across them.
Only negative numbers.
Negative numbers are the only ones that do it. Yep. And of course, if it's an equal sign, you can't flip an equal sign over, right? It's still going to be equal, so it doesn't affect it. Calm, cool, collected? Everything okay with this? Yes, Mr. Pro. Okay, great. All right. I don't remember. Are there fractions in today's stuff? No. Okay. Just remember, if there is a fraction in the homework, you're going to get rid of fractions the same way we've gotten rid of fractions every single time so far. If there's more than one, look for a least common denominator, distribute that least common denominator. If there's only one, well, it's very simple. You just distribute whatever's on the bottom. But remember, you cannot distribute a number to the inside of absolute value bars. Just reminding you of that. All right. Next example then. To be real with you, there's not much different going on here. It's just a secondary example. Positive case, negative case. It does say greater than a positive number, so this is a possible question. Just remember, you're always trying to do as little work as possible. So right up front, check to see if it's even possible. What if it says greater than -5? What would you do then? What would the answers then be? What would that be like? It'd be all of them. Yeah, all real numbers. Because every result from this absolute value symbol is going to be 0 or positive. So if this said greater than -5, you would do no work, and you would go, well, of course, whatever result I get is greater than -5. All real numbers. And if it said less than -5, you'd say no solutions. We're always checking up front for the easy, what I like to call low-hanging fruit. Can I do very little work and get the right answer? Always checking that first. So we're going to set up our positive case, which again just means drop the bars. Pretend they don't exist. And while I'm at it, I'm just going to go ahead and set up the negative case because why not? For the negative case, switch all the symbols on the inside of those bars. -2 plus 3x. And now we solve for x. Subtracting 2 from both sides here. And for this one, it'll be adding 2 to both sides because, you know, the 2 is negative. Remember, the symbol in front of a term belongs to that term. So this is -3x. For this one, we will be dividing by a negative number. This is going to be one of those times where inequality symbol has to flip over. Just be on the lookout for it. Usually a dead giveaway that you forgot to flip a symbol over is that your answer sets, the inequality symbols will point the same direction, which doesn't really make any sense. They're, as far as I know, they're going to always point in opposite directions, either towards each other or away from each other. If they ever point both to the left or both to the right, then you forgot to flip a symbol over somewhere. Go back and check for division by negatives or multiplication by negatives. What we get here is x is less than or equal to -1. And dividing by 3 here is just going to give us a fraction. Fractions are our friends. Do not panic. X is greater than or equal to 7/3. These answers don't overlap. This says numbers smaller than -1. This says numbers greater than a positive number. So they don't overlap. If we were going to write this as inequalities, we just put an or we just write or in between them, and you'd be finished. But we're going to be answering things like this in interval notation, no longer using inequality symbols. So when we go to write this as an interval, it's actually two different intervals with the U in between them that stands for the word union. It's another way of saying or, but it's a symbol instead of a word. So this says all the numbers to the left of -1, which means they never stop going left, heading all the way out to -infinity on the left side. Remember, you can never bracket an infinity because it's not a number. It's an idea, a goal that you will never reach. And we will climb all the way up to -1. Since it has an or equal to bar, that means including -1. Then we put a U in between them. It's not actually a U, it just looks like it. It's a union symbol. Beginning at 7/3, so bracket, because it's included, and heading to the right forever, all the way out to positive infinity, never reaching it, so parenthesis. When you write your interval answers with unions and stuff in between them, you should be going from small to big, just like in a single interval, you would do the same thing from small to big. So what do you think? Questions, comments, concerns? Anything I can clear up for you before we move on to polynomial inequalities? No? Okay. Remember, you got questions, you get them answered. Otherwise, I could have just kept the test this Friday, right? Slow down for a reason. I want to make sure that everybody is good at the material. Sir?
How do I know when to use the infinity again?
So when do we use infinities? So because we're talking about less than -1, you're never going to find a number that ends the numbers that are smaller than -1. You could always add a 0 to the end of it, 100, 1,000, a million, 10 billion, 10 quadrillion, negative obviously. So because we're never going to stop going left, -infinity, and because we're never going to stop going to the right, positive infinity. And that's how you know. Now this one didn't involve infinities because these numbers overlapped. If you were to draw a number line and shade them in, you would have come to a stop on the left side at -4 and a stop on the right side at +12. But that's because they overlapped. So if they don't overlap, you're going to be using infinities because that means they're pointing away from each other on the number line. So a quadratic inequality is started the same way solving a standard quadratic is. Hopefully, that's fingers crossed, factoring. Hopefully it factors. Because if it doesn't, you're playing with the quadratic formula and that's no fun. Don't worry, it factors. And this is actually one of the easy, what I like to call the easy ones, the shortcut method, because there's no number in front of x squared other than the value of 1. So when we go to factor it, we don't even have to do the whole Lizzie method thing where we have to say over a and then reduce our fractions. We don't have to do any of that. All we need to do is figure out what two numbers we'll multiply to. -30. And we need those two numbers to add to +1. And there are two numbers that multiply to -30 and add to +1. Shout them out. Yeah, 6 and -5. There we go. Let's switch it up. Move to purple just for funsies. Two sets of parentheses. And I am still going to be putting this less than symbol, but what we're doing at this point is pretending it says equals. That's what we're doing. Because we're trying to find the zeros, the places where this quadratic would have crossed the x-axis if we were going to graph it. We get x plus 6 and x minus 5. Of course, the order of these parentheses is unimportant. That does not matter. What we're going to do now is figure out what makes the insides of our parentheses equal 0, finding the zeros. But because this is an inequality, these zeros are now something that we call critical values. Critical values are numbers that make things equal 0 or make things undefined. Well, this is a polynomial. It's never undefined. So our critical values here are only the places where it equals 0. We will identify our critical values at x equals -6 and x equals +5. Do not fall into the trap of writing x is less than -6, x is less than 5.
This is for you from the Teaching Academy.
Awesome. Thank you.
Welcome.
Don't fall into that trap. Because remember what I said a minute ago? inequality answers, the arrows should never point in the same direction. So if you said x is less than -6 and x is less than 5, your arrows point in the same direction and you have a problem. What you do for this, once you have critical values of an inequality, is you draw a number line. We are going to create what is called a sign diagram. It's a shortcut around having to actually graph this quadratic. So we draw a number line. Picture not drawn to scale because who cares? It only needs two values on it. The critical values you found, -6 and +5. Before we move on, let me explain to you what we're doing here. We are going to decide where this parabola would have been, well, I'm shaking like a leaf, where this parabola would have been above the x-axis and where this parabola would have been below the x-axis without actually graphing it. This number line represents the x-axis. Our x-axis has been cut into 3 zones by these two numbers. A zone to the left of -6, a zone between our two numbers, and a zone to the right of +5. We pick a number from a zone, from each of the zones. We're going to do them one at a time. A representative number from that zone, and it does not matter what value you choose as long as it fits in that zone. So here, when we check a number to the left of -6, we can pick anything we want. I'm just going to go with -7. Now, there's no work to show for this. So this is one of those times where if you weren't here, you definitely need to be seeing this video. You want to be here, and you can write whatever you want to write for the procedures for this if you'd like to. I'm going to take the number -7, and I am going to plug it in here and here. But I don't actually care what the numeric value is. I just want to know, will I get a positive result or a negative result when I plug in that -7? So you look here. If you plug in a -7 right here, -7 plus 6 is a negative number. Can we agree to that? I don't care what its value is. All I care is that it's negative. And when I plug in a -7 right here, I get -7 minus 5. Again, I don't care what the value is. All I care is that it's negative again. And if I were to multiply those two negative results, I would get a positive result. That means every single number to the left of -6, if I plug it in, is going to give me a positive result. We do the same thing between -6 and 5. 0 is our friend also. 0 is very easy to plug in because all you have to do is just pretend that there's no x's at all. But if you drop a 0 right here, this left set of parentheses is positive. And you drop a 0 right here, 0 minus 5 is negative. If you were to multiply that positive number and negative number, you would get negative result. And then obviously, check the last region. Any number bigger than 5. 6 feels good. 6 feels good. 7, 8, 9, 10, doesn't matter. Any number bigger than 5. I'm going to go with 6. 6 plus 6 is positive. And 6 minus 5 is positive. And obviously multiplying two positive numbers gets you a positive result. Our sign diagram is filled out. What have we done? What we've done is we have figured out where this parabola is above the x-axis and below the x-axis. Normally, doesn't it say y equals, it could have said y equals x squared plus x minus 30, right? You would have plugged in any x you wanted and you would have gotten a y value as a result, correct? And those y values could have either been positive or negative. You just figured out where your y values are positive and where your y values are negative. And we were on the hunt for numbers that are less than 0, aka negative numbers. Our negative numbers were found right here. Anything between -6 and 5, when we plug it into this quadratic, will give us a negative result, and negative numbers are less than 0. So our solution set is from -6 to +5, and since it does not have equal to bars, -6 and +5 are not part of the solution set. Why, Mr. M? Because if we plug in -6 or 5 way up here, what we get is 0 is less than 0, which is not true. Sign diagrams are a big deal. We will use them a lot this year. So if there's something about this you need cleared up, please say something. Let me help you. I mean, there's more on the back, obviously, but we might as well get the questions addressed before we go on to the back. It's probably the first time you've seen a sign diagram used, I would imagine. Some of you have seen them. It depends on who the algebra honors teacher was or if you were in advanced topics last year, but they're a big deal. Okay. Well, should a question arise in the next couple examples, feel free to raise a hand. So let's do it again. Wait, there it is. Found it. So in the last example, yeah, we factored. But the reason why I jumped straight to factoring is because there was a 0 on the other side of the inequality. Just like polynomial equations, you can't solve them unless they're equal to 0. So this 20 can't be here. We need to bring it to the left side. Subtract 20 from both sides. It doesn't have a like term on the left side, so I just kind of wrote it wherever the heck I wanted to. You know what? I'm going to give this pink pen some love. Here we go, Amazon Basics. We get 2x squared plus 3x minus 20 greater than or equal to 0. And yeah, that is going to factor by way of the Lizzie method. So this at least give me a chance to review my Lizzie method with you. At least I think it will. I might have goofed the math a little bit. Whoa. 2 times negative 20 would be negative 40. And I'm looking for the two numbers that will... Nope, it works just fine. Okay. So we have to figure out what two numbers multiply to our a times c, which is 2 times negative 20 or negative 40. And I need those two numbers to add to my b value, which was positive 3. And yes, there are two numbers that multiply to negative 40 that add to positive 3. Yep, the numbers are 8 and 5, but clearly one has to be negative. So we're going to say the 5 is negative. That way they add to a positive 3 still. So 8 and negative 5. Those do add to 3, so we're in business. Remember, please, when you're doing this Lizzie method, you cannot forget the over a. The over a is what makes this method what it is. So we write our two sets of parentheses, putting the greater than or equal to symbol there, and x in the front of both of them, and then the numbers we found, positive 8 and negative 5. But we have to account for the fact that there was a 2 on the front of this thing, so we will say over the a value of 2. Now 8 over 2 reduces to 4. And this won't reduce at all, so we're just going to leave it alone. If we were just trying to factor, and we weren't trying to solve, the last thing we would do is take this 2 and scoot it in front of this x so that it said 2x minus 5. But because we're trying to solve, we don't need to do that. Was that a question almost?
Yeah, I was going to ask, so why are
We aren't, only because we're trying to solve. So you know when you're solving by factoring, at the very last thing you do is you say whatever's on the inside set it equals 0 and solve, right? So if you set this, if you move the 2, it says 2x minus 5. If you set 2x minus 5 equals 0, and I'll just do it up to the top right in pencil.
it would end up being x equals 5?
Yeah, because you're going to have to add the 5 and then divide by 2. So we're getting there a little bit faster by leaving it in this format, intercept form. If you do move the 2, there's absolutely nothing wrong with it. It's good factoring skills. You'll still get the same answer. So we have x, a critical value for x being negative 4, and a critical value for x being positive 5 over 2. And we're going to do the exact same thing we did a minute ago. We're going to take our critical values, we're going to throw them on a sign diagram, and we're going to check for positive and negative. I'm running a little low on vertical space, so I'll scoot over to the right. Picture not drawn to scale because who cares, it's unimportant. Negative 4 and positive 5/2. Once again, our x-axis has been chopped up into 3 zones. We're going to check all 3 of them. And when you're checking for positive and negative, check it here, because this is where you see what kind of numbers you're going to get when you plug them in. Am I going to get positives or negatives? This is where you look. Any number to the left of -4. -5 feels fine. -5 plus 4, that has a negative value. -5 and then subtract some more stuff, negative value. And multiplying two negatives will always give you a positive result. Any number between -4 and 5/2, man, I like 0. 0 is our friend. We have lots of friends in mathematics. 0 is one of them. 0 plus 4 is positive. And 0 minus anything, that's a number. That's not 0, is going to be negative. So 0 minus 5/2 is negative, giving us a negative result. Mr. Graham, I think I'm seeing a pattern. Can I just assume that that last zone is positive? No, I'm sorry, you can't. Do they usually oscillate between positive and negative? Yes. Always? No. And when you've gotten really good at using sign diagrams, you will start to figure out when it's going to happen and when it's not. So until you have mastered these bad boys, the strong suggestion is just check. It's not going to cost you anything. Any number bigger than 5/2. 5 divided by 2 is 2.5. So I'm just going to say 3. I could have said 10, 20. It doesn't matter. 3 plus 4 is positive. And 3 minus 2.5, still positive. Okay. This time, we were trying to figure out where our quadratic had positive results. Don't look here. Look here. Trying to figure out where our quadratic has positive results because positive results are bigger than 0. That's to the left of -4 or to the right of 5/2. Why did I say or? Because they do not overlap. So this will be written as two separate intervals with a u in between them. Numbers never stop going to the left, ever. So everything to the left of -4 would imply negative infinity, which we know we can't bracket, and coming all the way up to -4. 0 is a solution. Is 0 greater than or equal to 0? Yes, it is. So because we have an equal to bar, this -4 is included. Bracket. We will now hop over to the next set, which begins at 5/2, which is where it was equal to 0, which is a solution. So bracket your 5/2 and never stop going to the right. Positive infinity, never bracket an infinity. Talk to me. Any questions at all about sign diagrams, how to use them, why we use them, alternate ways, anything? Is that a question right there? Nope. Okay, just making sure. All right, guys. Well, then we will move on to the last example of today. And if I have time, should you have homework questions for me from any of the assignments we've already done, especially if you haven't turned it in yet, that'll be a good time to field those questions. Last one is not a quadratic. It's a cubic. That doesn't change how we solve them, though. We still start the same way. Factoring is our friend. It's got lots of friends. Now we're going to have to factor. The very first step to any factoring questions, every single time, look for a GCF. This one does have a greatest common factor. All three of those terms can give up an x. So the first thing you're going to do is, I'm going to do this one in green, it feels good. First thing you're going to do is you're going to pull an x from the whole thing and bring it out to the front, leaving us with a quadratic. X squared minus 8x plus 12. This is one of the shortcut ones because there is no number in front of x squared. That means we can jump directly to the what two numbers multiply and add to business. -6 and -2 are going to be the two numbers that we're hunting for. Those two numbers will multiply to positive 12. and they will add to negative 8. Negative 6, negative 2. Now, the order in which we write our parentheses is unimportant. I like to put my smaller stuff first. Doesn't matter. This polynomial has been factored, and it has 3 critical values. You have a critical value everywhere there's an x, and since there's an x in 3 different places, there are 3 different critical values. Anytime you have an x that sits out in front, and I don't care if any numbers are out there with it, it wouldn't matter what was in front of this. I could put a 2, a negative 16, a pi over 7, it doesn't matter. As long as there's an x outside the parentheses, you will always get the same result there. Its critical value has a value of 0. Yeah. Anytime you got an x sitting out front, its critical value is automatically 0. And then for the other two, just do the same thing we've been doing, and that is to switch the sign. So x equals positive 2, and x equals positive 6. Our sign diagram has 3 values on it, and again, picture not drawn to scale, because we don't care. We're just going to draw a number line and throw 3 digits on it, and check the 4 zones those 3 digits created. All that matters is that you put them on there in the right order. And yes, we do have 4 zones. We're going to check all of them. A number to the left of 0, that's any negative number we want, like negative 1. Now realize, now you have to worry about 3 different things. Dropping a negative 1 here gives me a negative. Negative 1 minus 2 is negative. Negative 1 minus 6 is negative. 3 negative numbers gives us a negative result. Basically, we're just looking for, is that an even number of negatives or an odd number of negatives? Grab any number between 0 and 2. 1 fits nicely in there. 1 is positive. 1 minus 2 is negative. 1 minus 6 is negative. A pair of negative signs gives us a positive result. A representative between 2 and 6, doesn't matter which one. 3. 3 feels good. 3 is positive. 3 minus 2 is negative. 3 minus 6 is positive. I can math. I swear I can. 3 minus 2 is positive. Just testing you. Just making sure you were thinking. And 3 minus 6 is negative. Right? Yes. Okay. Just making sure I can still subtract this morning. And a single negative sign gives us a negative result. Last, any number bigger than 6. 7. 7 is positive. 7 minus 2 is positive. 7 minus 6 is positive. Positive result. Mr. M, are you sure that they don't always oscillate? Yes, I'm sure. Okay? Just trust me on this. When I introduce sign diagrams, I might as well show you ones that oscillate. But there are times when they don't. And we will get to those. It's not quite yet. What were we looking for? We were looking for numbers that are less than or equal to 0. So those are our negative results. To the left of 0, between 2 and 6, equal to bar means 0 as a result is okay. Yes, 0 is less than or equal to 0. So brackets. So numbers to the left of 0, well, there's nothing at the very end of the left, so we say negative infinity. They will never stop. Coming all the way up to the value of 0, bracket because included, the equal to bar. Union, hop over to your next set. Your next set of negative numbers happens between 2 and 6. And again, because equal to bar, they are both included. And that's all she wrote. What do you think? Absolute polynomial inequalities, not too bad with sign diagrams? Yes, ma'am.
How do we know that it's really negative infinity?
How do we know? So,
To the left.
so are we saying how do we know that I have to write this, or how do we know that this zone was an answer?
That zone.
We knew this zone was an answer because we were hunting for numbers that were less than 0. So any negative number would be less than 0.
Oh, okay.
It just it's just a coincidence that this is a 0 and this is 0.
Okay.
That's complete coincidence. Yes, sir.
What if the x's didn't cancel?
What if the x's? You mean if x wasn't a GCF?
Right.
So we will learn how to factor trinomials that do not have x as a GCF later in the year. You might have learned it in Algebra 2 Honors. You have to use something called the rational root theorem and Descartes' rule of sign and synthetic division. Some of you may have learned that stuff. No synthetic? Yeah. So you would have used Descartes' rule of sign and the rational root theorem, and that's assuming it could factor. But we'll get to that later in the year. For now, if it's a cubic, it factors with a GCF. For now.